Learn like a pro.
All right, let's get right into it. Today we're going to tackle a really fundamental question in chemistry. What actually makes a chemical reaction go fast or slow? I mean, have you ever really thought about it? It's the exact same stuff, right? But one just sits there while the other vanishes in a flash. Well, the answer to that little kitchen mystery is actually the key to understanding basically every chemical reaction in the entire universe. See, to understand speed, you've got to know the rules of the game. And in chemistry, that rulebook is called the collision theory. It's a surprisingly simple idea that explains everything from why an explosion is so fast to why a rock takes centuries to weather away. Okay, let's break this down, because every single word here matters. The theory says that particles, atoms, molecules, all that stuff, they don't just magically change. They have to physically slam into each other to have any chance of reacting. But here's the catch. Not just any little bump will do the trick. For what we call an effective collision, one that actually leads to a reaction, two things absolutely have to happen. First, obviously, the particles have to collide. But second, and this is the big one, they have to hit each other with enough energy. There's a minimum amount of energy needed, and it's called the activation energy. You can think of it like a "you must be this tall to ride" sign at an amusement park. If the particles don't have enough energy when they collide, they just bounce off each other, and nothing changes. Okay, so if we need these effective collisions for a reaction to happen, a pretty logical way to speed things up is to just make more collisions happen, right? Increase the odds? So let's look at a few ways we can rig the game to boost that collision frequency. First up, we've got concentration. This visual here makes it super clear. On the left, with a low concentration, you've got a few particles just kind of floating around. Yeah, they might bump into each other eventually, but it's not very likely. Now look at the right. We've jammed a ton more particles into the same space. It's like going from an empty hallway to a packed concert. You're basically guaranteed to be bumping into people all the time. And the result of all that bumping? Well, more collisions mean more chances for an effective one to happen. And when we plot this out on a graph, a faster reaction shows up as a much steeper line or a steeper gradient. Burn that image into your brain. Steeper line means faster reaction. Now, for gases, we have a very similar trick up our sleeve. Pressure. When you increase the pressure, you're essentially squeezing those gas particles into a smaller box. And just like increasing concentration, you're forcing them to get up close and personal, which means, you guessed it, way more collisions and a faster reaction. Okay, so back to that sugar cube mystery. When you're dealing with a solid, the reaction can only happen on its surface. For a big lump, like our sugar cube, most of the sugar molecules are trapped on the inside, totally unable to react. But if you crush that cube into a fine powder, you suddenly expose all of those inner parts. You haven't changed the amount of sugar, but you've massively increased the total surface area that's available to react. And the result is exactly what you see in your coffee cup. A larger surface area means there are way more spots for collisions to happen all at once. This cranks up the frequency of effective collisions, which makes the reaction go much faster. And if we were to graph it, we'd see that same signature steep curve again. So far, we've just been talking about making collisions happen more often. But what if we could make each collision more, effective? What if we could make them more powerful? Let's talk about turning up the energy and finding some clever shortcuts. Temperature is a real powerhouse because it gives you a 2-for-1 punch. First, when you heat things up, the particles get a jolt of energy and start zipping around way faster. That alone means they're going to collide more often. But, and this is the really important part, they don't just collide more often, they collide harder. A much bigger fraction of those collisions will now have enough power to clear that activation energy hurdle we talked about earlier. And to put that into perspective, get this. A pretty common rule of thumb in chemistry is that for every 10 degrees Celsius increase in temperature, the reaction rate can actually double. That is a huge effect from a pretty small change. Okay, but what if you can't just crank up the heats or add more stuff? Well, then you might use a catalyst. A catalyst is like a chemical shortcut. It's this amazing substance that jumps into a reaction and shows the particles a totally different, easier route to take, one that requires a lot less energy to get started. And the coolest part, it doesn't even get used up in the process. And this chart just lays it all out. Without the catalyst, the reactants have to climb this massive energy mountain, the activation energy. Most of them just can't make it. But when you add a catalyst, it turns that mountain into a little hill. It literally lowers the activation energy, so now a whole bunch more particles have enough energy to make it over the top when they collide. You know who's the absolute master of this? Nature. Inside your body, right now, are thousands of these natural catalysts called enzymes. They're these super complex protein molecules, and they're responsible for making all the chemical reactions of life happen at a speed that can actually sustain you. But enzymes are kind of picky. They are incredibly specific. The enzyme that breaks down sugar won't even look at a fat molecule. It's often called a lock and key model for a reason. They're also really sensitive. If you change the temperature or the pH even a little bit, their delicate structure can unravel and fall apart. That's called denaturing, and once it happens, the enzyme is basically useless. All right, that was a lot. We've talked about making particles collide more often, and we've talked about making those collisions more powerful. Let's just pull it all together for one final clear recap. This table right here is your cheat sheet. It's the whole story. On one side, you have the things that boost the frequency or number of collisions. That's cramming more particles together with concentration or pressure and increasing the surface area. Then on the other side, you have the things that affect the energy of those collisions. Catalysts do this by lowering the energy needed. And then there's temperature, our special case, which does both. It makes particles collide more often and with more energy. No wonder it's so powerful. So when you boil it all down, it's this simple. Controlling chemical reactions is all about pulling two main levers. You can either make particles collide more often, or you can make them hit harder. Everything we've talked about, concentration, temperature, catalysts, it's all just a way of pulling one, or sometimes both, of those two levers. So my question to you is this. Now that you know the rules, now that you know the levers you can pull, how would you go about designing the fastest reaction you could possibly imagine? Thanks for tuning in.